Today, I want to finish up with the solar cycles and magnetism. We got a little bit pinched at the end with respect to talking about how magnets work. So I want to make sure that that is cinched it down because we're going to keep talking about magnetism in this course, and we need to make sure we grasp it fully. Otherwise, this will be the last day that I am going to really harp on about the uh, let's say this the solar structure, at least with respect to the outer layers of the stars. It will keep coming back up again. But before we move on from this, I wanted to take some time to review kind of the history of how the scientists came up with this picture of the sun that they have today, because most of the work was done back in the late 1700s, early 1800s, and people kind of concluded some things at that time and moved on from it. And I want you guys to see a bit what that looked like, because without understanding it, it's a bit tricky to comprehend how in the world we're left with the pickle that we're in. Um, Now, before I do all of that, I want to make sure that I give you guys a chance to get some attendance participation points here and simultaneously make sure that everybody got the main take home messages from last time. So, can you tell me something, either that you remember from last time that was interesting or something that didn't make sense so that we can clarify? Because it didn't make sense to you, it probably didn't make sense to somebody else. Yeah, and tell me your name, by the way. I haven't learned your names yet. Which Alex? Gotcha.
that I talked about last class is how diamonds are both made of carbon, but because they have different lattice structures, it makes them different. So I just thought that was interesting.
Yeah, that's extremely huge. And this is the last class I'm going to bang on about that, but I want you guys, and actually, we'll come back to it when we talk about white dwarfs. But um, this principle is extremely important, and that's why I'm going to spend most of the class today talking about the history, because people didn't have access to the data that we do today when they were coming to these conclusions, which is how we got where we're at. It's really important. So yeah, thanks for that. Yes.
And also, I kind of found interesting about how we talked about how the sun has different layers, like a big gaseous sandwich.
Mm.
Also, sunspots. We could see them. That was wild. But he's actually.
Yeah, they change. We'll talk more about that in a minute. Um, yeah, the layered thing is quite interesting as well. Um, what do I want to say about that? We'll come back to the layered thing. Remind me your name again before I move on. That's right. I'm gonna actually have to start calling on people at some point because I want to make. I've got some folks I haven't hit yet. Isabel, what's your last name? I got quite a list here. Cooper. Gotcha. All right. Who else? I'm trying to call on people I haven't talked to yet. Yeah. Next. Yes, you in the purple. Courtney.
So the sun, I thought it was really interesting that the surface of the sun is always producing wind.
Yeah, let's we'll talk a little we'll have time to talk more about the wind, but it's actually it's an outstanding issue for astrophysics in general, because there's a couple types of wind, and it's explained in a really interesting way, which is something like it's very much like the sort of sublimation event that you think of when you see dry ice, right? Going from one phase to another very quickly. It's very, very strange though, because it actually gets faster the further it moves away from the sun, which is really hard to comprehend on an intuitive level. So, if you would think about something being thrown, like if you threw a baseball away from the Earth, you wouldn't expect it to pick up speed as it moved away. But that's actually what happens with the solar wind. So it's a pretty strange substance, and we'll deal with that some more later in this course. Other thoughts? Yeah. Tell me your name. Yeah, tell me your name first. You're good.
Geotape.
That's right. Okay, Gio. What's your thoughts?
I thought it was interesting how our atmosphere only really lets through radio waves and the light that we see.
It's pretty bizarre, yeah. It's another example. Have you guys ever heard of the anthropic principle? Anybody ever heard this word before? This is this idea like you know, everything seems to be perfectly tuned for us to exist in this universe, right? If the universe was, say, a little bit colder, a little bit hotter, you know, we wouldn't be able to be here. And if the Earth was a little bit closer to the sun, a little bit further away, it wouldn't be a very fun place to live. And this is another one of those strange just so situations where we can see really nicely because all this light comes down from the sun in this perfect range that our eyeballs are tuned to. And so I'm sure there's an evolutionary argument to be made there, but you don't see a lot of animals that can see, or even obviously humans, but you don't see anybody really who can see in the radio wave length. So that's pretty bizarre, I think. Maybe they do, and we just don't know about it. But nobody seems to be using radio waves, despite the fact that they do make it down to the surface of the Earth from the sun and everywhere else. Pretty bizarre. What else? Yes. Tell me your name. All right.
I thought it was interesting that the sun's magnetic pole changes every 10 years and trying to look how that affects the Earth.
Yeah, I want to talk about that to start in just a second. The mechanism by which that happens is a little bit mysterious still, so I want to explore a couple ideas with you guys. So yes, that's a good point. Let's talk about that some more. Who else? Yep, in the back. Tell me your name. Gotcha.
Layers of the sun. I think it's kind of cool that well, the sun's filled with like liquid hydrogen it is, or
Well, it depends who you talk to, I suppose. Yeah.
I think it's cool that we can see that now.
Yeah. So right now, and this will, you know, wish I could teach a whole class on this, but right now we've built the sun off of we've built basically our model for how fusion works, how the sun powers itself, and so much else off of the ideal gas equations that you guys learned in intro chemistry in high school, basically. I'm going to talk about how that happened and why people did that. But at least to me, it doesn't make a ton of sense, particularly on the very simple evidence that you can't get a continuous spectrum from a gas. And so that's a really interesting crux. I know you guys are probably like, why in the hell is Dr. DeLay going on about this so much? It will make sense because so much of the astrophysics that we're going to see downstream of this in the cosmology, the story for the universe we built upon that, actually comes down to this single revelation, which is, you know, what is the star made out of? What is its actual structure? And then based on that, what can it do? You know, we're going to see some fantastical stories later in the course of, you know, exotic phases of matter and incredible, you know, world-swallowing black holes and stuff like this. Those conclusions are based on the idea of an infinitely compressible substance, i.e. a gas. And so if the stars are not made out of gases, then all those possibilities go out the window with it. Yes?
I thought it was kind of interesting how the sun's like putting off way more energy than like the Earth could ever use. And,
Yeah, in a lot of ways, huh?
yeah, but I'm like, I was wondering where all the extra energy like is going. It's like we're like such a small part of like the sun's whole like thing it has going on. And we're just like a weak little thing that we're using just like a tiny bit of it.
Yeah, I often wonder about that too. You know, I don't think people have a great sense of how all that works out. I haven't seen. So I wish I could think of the image to pull up. There's this really wonderful. What's the name of this? I actually have it on my phone. It's called swpc.noaa.gov. Let's see if we can find this. Oh, come on. So the sun is constantly shedding little pieces of its outer surface. And there's a really beautiful website where you can actually watch a reconstruction of this from the top down. Let me see if I can, oh, very close. Here, dashboards. Space weather enthusiasts, that's us. And here we go. So the sun's relatively calm right now, so that makes for a less than ideal picture of this thing. But what you see here is the sun's at the center. It's spraying different densities of its solar wind outward. And then occasionally, let's see if I can play this. This is actually it includes today, but it's also a projection of what is expected to happen in the next few days. Let's see if we can see this. What is going on? Absolutely nothing. Or is it just loading? No, it's just loading. Okay, so you can see a side view here, and you can see a top-down view over there. We have just this kind of regular stream of ionized hydrogen flying off the sun, the wind, let's say. But occasionally, a big chunk of that will come off, and it looks like, almost from the top down, it looks like a big chirp, like an echo moving out. And presumably, that chunk of material is flying off into interstellar space. And presumably, all the stars are doing this all the time. Every once in a while, we'll get a space weather alert, like there's an incoming solar storm, and we have to watch out for something like this. It's actually, so I think it does open that question of like, well, what happens to all of that discarded material? Where's it going? Is it being reused by the other stars in some sense? I think those are really good questions. The problem for us on Earth is that when the sun kicks off these big blobs of material, they can really mess things up for us, particularly because we have a highly electronic civilization at this point. So the last time that there was a really nasty chunk of the sun that flew off, call it a coronal mass ejection. Last time this happened was in the 1800s. Now, the last time it happened and it hit us was in the 1800s. It happens all the time otherwise, but of course the Earth's got to be in the exact right position because it's a very directional outburst from the sun. This must have happened throughout history. I was trying to find some records before class of people in antiquity having recognized this, but they didn't. They were aware of the sunspot cycles, but we'll talk about how that relates. But in the 1800s, there was this event called the Carrington event. And the only reason people noticed this, I think, is because it was the birth of telegraphs. You guys know what telegraphs are? Other than the app? Just a simple wire system by which you transmit electrical pulses. And I believe they were using Morse code of some sort to essentially just transmit little bleep. Yeah, help me out.
There's also two types of telegraph.
Oh.
There was the original telegraph in France, which
There's arms that like move.
Huh.
and then there was the telegraphs you're thinking of.
What were the arms all about?
They wanted, it was like a flag system they were building on land. So each arm movement had a meaning, and it would go from the next to the next to the next to the next to the next before the telegraph that you're.
Far out. Interesting. So it was like telling the next system what the arm position was.
Yeah, but it had to be manually changed by someone at each point.
Nice. Wow.
And that was in France.
All right. Well, these telegraph systems apparently became super overloaded during this solar storm that happened. So we have this, we talked about it last semester more, but the Earth has the benefits of having a really, really effective magnetic protection system around it. One of the is it the strongest? I guess Jupiter's is stronger, but it is an abnormally strong magnetic field considering the size of our planet. And this shields us from most problems, but it can become overwhelmed, especially when the sun kicks off large chunks of its material from the surface. And so this is what happened in the 1800s, and I guess it crashed all of these. It caused, fires in the telegraph stations and burned up all of these lines and stuff. We haven't had anything like that since we've had the internet or telecommunications systems, stuff like that. And so it's a very real concern. Last time I was talking with anybody at NASA, this was on, this was where the sessions were at, was like, how do we actually get around this? And a lot of it is figuring out how to isolate different power grids from one another, because of course, a coronal mass ejection from the sun's only going to hit one side of the Earth, or one part of the Earth at a time. Right now, I don't know if you guys realize it, but like our power grid is hooked up to the next power grid over, which is hooked up to the next power grid. Everybody's kind of interconnected, which is nice because it means when we're not using a lot of power, somebody else might want to draw on the same power plants. So it's really good to be interconnected, except when there's an overload of the power grid. So all of these statecrafters are trying to figure out how to power down and isolate individual power systems from one another in the event of these coronal mass ejections. which you typically have something on the order of several hours to prepare for the impact of. So we haven't had to stress test that system yet, but it's going to be really interesting. I imagine it will happen in your lifetime. So we'll see. That will be really interesting. All right. Let's ditch this for now. Sorry the sun's so boring right now. We can show you guys something interesting if it does happen. What else do we got, guys? Anybody else want to chirp in? I'm going to just like call on a couple of people otherwise. Yeah, in the back. Tell me your name. Jaden.
I found the solar cycle was pretty interesting.
What about it?
Exactly what it does.
It's pretty weird because it's really poorly understood. So we get a lot of sunspots every 10 years, then we get a little bit of sunspots, then we get a lot. The magnetic field reverses of the sun. It's very, very interesting and bizarre. And yeah, I'll get into some mechanisms for that in just a second. A couple more people. Anybody else want to talk? Say hi. Anybody confused about anything? Yes, please.
We sort of talked about, or I found it interesting when we talked about like black bodies and black light and how it was mentioned slightly earlier how different types of light get absorbed by our atmosphere, so we can't see those light. And it's interesting to think about, since all we have really to go off of is light, like what are we missing that we can't see just because it blocks light as well?
Yeah, well, we have to put telescopes in space for that exact reason. That's how we get the best data. But yeah, there's little, atmospheres absorb, the sun's atmosphere absorbs light too. That can be really useful because it tells us exactly what molecules are in the surface, or not in the surface, in the atmosphere of the sun. It's going to be really important when we start looking at other stars and we start trying to make, let's say, this is something we love to do in science, right, is group different, like especially in biology, we group different organisms together, call them species, and they're in families and all of this. We do the same thing with stars. And we try to come up with a coherent story of where all these stars came from, where they're at in their lives. A huge part of that is analyzing the black lines, so the absence or the light that's being screened out by their atmospheres, and also their black body spectrum, which tells us their temperature. Sort of. Tells us their temperature. It certainly tells us something about their color. One thing I didn't get into enough that I probably should have is that the black body, a black body temperature, so we have this ideal chamber, which was developed primarily by this gentleman named Kirchhoff back in the 1800s, where he was doing all this work in characterizing the spectrum, the different colors, the continuous rainbow that emerges from heated bodies, essentially called black bodies. One of the characteristics that allows you to tell the temperature of a black body in a laboratory is that the entire system's at thermal equilibrium. That means there's no heat coming in or out of the system. The problem is with the sun, as we've talked about, there's these huge convection currents on the surface of the sun, right? You guys remember like the kerneling pattern on the surface of the sun that we looked at this photosphere? Those are really well accepted and super high energy convection systems where there's a lot of heat transfer going in and out. The interior of the sun presumably is really hot. It's cooling off as it reaches the surface. And so the only, all of the heat that we're able to assess from the light on the photosphere is devoid of whatever heat has been lost to that convection process. What does all this mean? It means that when we say that by a black body temperature, the surface of the sun is, say, 5,800 Kelvin, it means that it's 5,800 Kelvin in its rays, its light is 5,800 Kelvin, but it doesn't add in all of the heat that's taking place when all those molecules are moving around and grinding against one another and so forth, right? Because the sun is not at thermal equilibrium. Obviously, you go outside, you get cooked by the sun. It's giving you some energy as it does that, right? So it's a very far from equilibrium system. And so whether the surface of the sun is actually at that black body temperature, it's probably not. It could be actually wildly hotter, but we wouldn't see that in the light because the temperature or the heat is being taken up in other processes like that convection. Hope that makes some sense. All right, anybody else? One more, two more? Yes. Gotcha.
Before the class, I and
reading the textbooks, I didn't know the auroras come from the sun.
Oh yeah, yeah, indeed.
So I was thinking that was very interesting. And I was curious why the colors are all different.
Mm. Yeah. So they do in some sense. The auroras was the question. Have you guys anybody seen the auroras before? Oh wow, I'm jealous. Really? Gosh, I missed it. I did not see them, and I've never seen them, and I'm jealous. Um, so yes, the interaction of the solar wind actually with our own atmosphere way high up, where we have really, really thin atmosphere. It's easily ionized, right? Remember, gases that are depressurized can become ionized really easily. That means they conduct electricity really well. And so what you're seeing is essentially the same idea that you'd see in a fluorescent light bulb, only those colors are going to depend largely on the elements that are getting ionized, so the oxygens and the neons and stuff like that. That's getting lit up like a fluorescent light bulb, basically. Not the fluorescent part, but like a gas lamp, basically. So that's really cool stuff. And actually, during that Carrington event that I mentioned, right, when there was a huge solar storm, the auroras reached way, way down into the lower latitudes, right, because it was so intense. So auroras are really cool. I really hope I get to see them at some point without having to go someplace really cold.
That's July, I would say.
Yeah? Must have been a solar storm, huh?
He drove out on it to like Immigrant Lake. And apparently you couldn't see him super well with the naked eye, but he said he took a picture with his camera.
Like a time lapse type thing? Like overexposed it? Man, that sounds good. Wow, cool. So cool. Yeah, so solar storms can be beautiful. They could also be disastrous. Hopefully we'll see more of the former. Cool. All right. I still have not made it even halfway through this list for a second check, but that's okay. I guess we can keep rolling. Any last confusion that anybody wants to clear up before we move on? Nobody really talked about magnets. That's probably because I was going too fast. Yeah.
Solar flares when they're let off, and how Earth's magnetic field shields us from that. I saw like in one of the videos, it looked like the shield of magnetic layers on the Earth was like that in layers and kind of split apart and joined it. And you go into that.
Like the tail of it. From what I understand, so I mean the atmosphere itself is okay. So the Earth itself is in some sense in the slipstream of all of that wind that's going by, right? And so there's going to be some laminar flow as it goes over. You can think about it as like if you ever put like an egg under the faucet or something, right? It's very smooth over the top of it, and then there's going to be some like churning and turbulence behind it. The turbulent region behind it actually allows for some of that wind to slip back in, and so you might be referring to something like that, where you're actually kind of making a cavitation on the backside. And of course, the actual specifics of the magnetic field of the Earth, right? If we go back, I guess this is as good a time as any to kind of keep rolling with what we were talking about. Let's see if I can get this to work. So we were talking a little bit about how magnets worked last time. And generally, your textbook probably doesn't go much beyond like magnetic field lines, right? And this is reasonable. So magnetic field lines aren't real things. You can't go and grab a hold of a magnetic field line. What the field lines do tell us is the direction by which some sort of charged particle will move when it's, let's say, thrown into a magnet, the region of a magnet, right? So I tried to give you guys an idea of perhaps what the atoms might be doing, right? So how does this magic, does anybody remember anything about my explanation for magnetism last time? I sort of deeply regret having rushed through this. I probably should have just saved it for the beginning of class. Yeah.
Linda touched on electromagnets requiring iron in the center of the coil.
That's really important. Yeah.
I don't know, I wrote some crazy shit here. And the idea of our polar reversal has to do with our iron core tumbling over.
We'll get there in a second. What about magnets themselves? So they seem like magic, right? You can I don't have one here. We don't have any magnets in the room. So if you got a magnet, it can presumably pick things up, right? That are correspondingly metallic, right? Certain types of metals, right, can be picked up with magnets. What the heck is going on there? How is that possible? Is it just magic? Yeah, 11. That's right, man. That is exactly right. So, this part gets really lost particularly in intro chemistry. Actually, even in advanced chemistry and physics textbooks, it's often neglected that when we look at the atom, we talk about the atom as the outer part of the atom is called the electron. And it's usually drawn as this nice little bubble. Sometimes they get these really beautiful shapes, right? And when they're in higher orbitals, you get these, I don't know if you guys remember orbitals from chemistry. Everybody take high school chemistry here? Yeah, no, it's okay. It's okay if you didn't. But essentially, suffice to say that the electron is taken, at least by the chemists, to be the outer surface of the atom. The weird thing about the electron is that, most of the time, when you go looking for it with an instrument, you find it at a very predictable distance from the nucleus of the atom. It just kind of hangs out there, and it's difficult to say where it is. The idea of it being a sort of cloud, right? You don't know where you're going to be able to locate this shell is reasonable. The piece that gets lost is that actually you can find that shell at any distance, although your probability of finding it goes precipitously down the further you get away from the nucleus. But the reality of the situation, at least the way that I think is a healthy way to interpret this, unless you want to believe in magic, which is totally up to you, but I think that if you want to come up with some mechanism that actually makes sense for how the heck these actions at a distance like gravity and magnetism and light could possibly function, you have to consider that perhaps the outer part of the atom is in some rarefied form. I don't know what the structure of that would be exactly, but I tend to think of it as sort of like a furry outer coat on the atom. People will talk about the electron cloud as well, but clouds don't really convey tension in the same way as fur for me. So I think about it as having these kind of like hair-like projections from it. But whatever works for you, it's a visual tool. The point is that magnets, the atoms in one magnet and the atoms in the metal that's attracting, well, they're either doing it through magic or they're doing it because their surfaces extend in a way that you can't actually see with your eyes because it's very, very rarefied, very, very not dense. It's a word that I keep throwing up there. Okay, so the surfaces of the atoms are in some sort of motion. That motion lends itself to either attraction between its neighbors or repulsion, and it's mediated in some way that has yet to be completely understood. Why has it not been understood? That's an interesting question. Why do you guys think that, well, does anybody know why people don't worry about whether there's any sort of well, how about this? Do you know what the word mediator means? Anybody? Mediator? You guys ever heard of this before? Yeah.
Is it just like an unbiased spectator, or I don't know, right?
It's yeah. Go ahead.
Kind of as like I know it as a person who is kind of trying to settle an argument.
Yeah. Okay. That's totally reasonable. So when people talk about like the mediator of light and gravity and electromagnetism, that's kind of what they mean. They mean, how in the heck does one atom over on this side of the room convey a force to an atom on this side of the room, whether it's a magnet or a flashlight or whether it's just me sticking to the floor or falling through the atmosphere when I go skydiving or something, right? What is the mediator of that action? What is allowing me to be pulled to the floor, right? This was a huge topic in physics for most of the 19th century, leading right up into the early 20th century. Why did people stop looking for it? Does anybody have any idea? Because anybody? Go ahead, don't worry. You got an idea? Yeah.
Maybe they just decided it didn't matter.
Yeah, they decided it didn't matter. That's exactly right. That's exactly right. And the reason they decided it didn't matter is because they had really good math equations to describe what it looks like when I fall out of an airplane, what it looks like when a planet orbits around a sun, stuff like this. It's also coupled to a series of really important experiments that happened at the end of the 1800s. So the popular idea prior to these experiments was that there was this stuff, kind of like a magic fluid of some sort, that was everywhere called the ether, the luminiferous ether. You guys ever heard that word before? No? You never heard of the ether? Awesome. All right. So there was this stuff that you couldn't see called the ether, which was supposed to be the mediator of all of these magical invisible forces like light, gravity, electromagnetism, all of these things. There was this substance that was everywhere. And so it was outside of the earth, and it held us to the sun, and so on and so forth. So they went looking for it, and they designed some really ingenious experiments where they were like, okay, here's the thing. If the earth is flying around the sun at like a gazillion miles an hour, which everybody believes it is, there should be essentially, if we send a light ray, it should, kind of drift a little bit through the ether, right? The ether being the mediator of the light. The ether is that which is waving during a light wave, let's say. If we send this light ray and the Earth moves forward, then it's going to arrive a little bit behind where it set out from. Does that make sense? Right? If I'm, if I'm in a boat and I shoot a torpedo while I'm moving, right, it's going to fly off in that direction, and it's not going to arrive exactly in line with where I'm at, 10 minutes from now, right? Makes sense. This is kind of how they thought about light, too. The problem was when they did this experiment, they couldn't detect any kind of drift of the light signal in the ether. And they tried many, many ways, and they did many versions of this experiment. Some of them would detect a little bit of drift, some of them would detect no drift, some of them would detect positive, some would detect negative. Basically, it was just a nightmare of a result. And the whole world was working, the whole physics world was working on this. They couldn't find it. Now, the interesting assumption at the heart of all of these experiments was that the ether stuff, the mediator, was a substance upon which all the atoms were sort of floating. So there was the mediator and there was the atoms. And the atoms moved through the mediator. And so naturally you should see this kind of drift of these light signals and gravity signals and all of these things. And so they couldn't do it. Huge mathematical revolution came in with Einstein. We'll talk plenty about Einstein soon. And people basically decided they didn't need it. It didn't matter. They could design plenty of technology without it, and they moved on. What's really interesting is if you take what I'm telling you guys seriously about the nature of the atom and the electron, which is its outer surface, the interesting piece of that puzzle is that if the atom's surface is, like I say, actually quite rarefied, and you can actually find pieces of the atomic surface at quite serious distances from the atom, then the atom is taking its mediators with it, which means that you would never, ever detect a separate ether from the atoms themselves because the atoms are their own mediators in their extended form. So it's kind of interesting that people tried really hard to make sense of this by assuming that there should be a separate substance from the atoms themselves. Many, many years later, they do all of these experiments after the invention of quantum mechanics, and they determine that actually this electron has this extended structure, but it's too late. They've already moved on. Nobody cares. Nobody's doing work on this anymore. So anyways, magnets, not magic, in my own personal opinion. I think that the atoms are in fact interacting with one another through their own external structure of their own surfaces, which are extensive in nature. at the very least, it's a rational way to think about it that doesn't involve mysterious force fields and things like that. So back to the sun. These lines essentially tell us the directions upon which those forces will be applied. I think in reality, they're actually telling us about the cohesive, coherent motion of all the atoms involved in these processes. But what's really interesting is that the convection cycles, the churning of the hot material bubbling up to the surface on the sun, sets up these really nice, essentially solenoids. This is how we build an electromagnet. And the turning of the sun twists them into these loops, which we call driven by these Coriolis forces. It's the same process that gives us, let's say, hurricanes on Earth as well. The same process that determines which way your water goes down the toilet. So if you go down in the southern hemisphere, it goes the other way. Anybody ever been to the other hemisphere? Anybody ever been to the equator before? No? Okay. I went to Ecuador one time, and there's a really funny place because you can go on like one side of this, there's like a little park right on the equator, and you can go and basically pour water down like a little tub with a sink, and it turns one way, and then you go to the other side, and it turns the other way. It's pretty far out. That's essentially the same process that's spinning all this goop inside of the sun. By the way, it's also happening inside of our planet. This is actually, I think, a picture from a textbook about our own planet, but it's the same process. The result is that there's this powerful magnetism. Now, something really funny, I just started to get into this a little bit at the end of class last time, and you brought it up, that the poles reverse. They reverse really often on the sun, like every decade, and they reverse something on the order of 1 million years here on Earth. Now, it's anybody's guess what the consequences of that are here on Earth. But the mechanism is a little elusive in both cases. Now, the standard explanation for this, does anybody remember the explanation they give you in your textbook? It's okay, I forgive you. Anybody? You guys got to relax a little bit. So standard textbook explanation is something like this. So the surface of the sun does not turn homogeneously, right? Actually, the equator turns faster than the rest of it. So let me pull up a little picture of that. I'll come back to that. So the surface turns a little bit faster at the equator. The idea is that as this happens, it sort of distorts the magnetic field lines at the surface, which causes them to sort of tumble back on themselves. And periodically, the whole magnetic structure, let's say all those churning atoms that are creating those solenoid loops, gets confused, tumbles over, and you get a different structure. This is a challenging explanation for me because when you ask there's two reasons. First of all, the atmosphere of the sun, which is gaseous, does not exhibit differential rotation. That's because gases can't exhibit differential rotation. Again, if the sun is a ball of gaseous plasma, how in the world does it have differential rotation at the surface? I have no idea. It seems to make no sense. The other part that's really troubling about this explanation is that you ask, why is it supposed to be differential? The reason for the differential rotation is supposed to be the magnetic structures themselves. So it's kind of circular if the magnetic structures are causing the differential rotation, but then they're also the differential rotations leading to the magnetic reversal in the same at the same time. So I'm not sure. We also have a really hard time applying this model to something like a planet's magnetic field reversal, because we know that our planet has magnetic field reversals every 700,000 million years or so. We obviously don't have differential rotation at our equator. Otherwise, Ecuador would end up in the Mediterranean or something like that periodically. It would not be a good situation. So that doesn't work too well for me. But let's see here. This is kind of interesting. I apologize for guys who were in the class last semester. Has anybody ever seen this before? So this is from the ISS, the space station. And as you can see, what's gone on here is that there's a wing nut that this I believe it's a gentleman, but it could be a lady. This person has detached from its socket. And what's really interesting is that completely on its own, this wing nut inverts its polarity periodically. Now, there's a highly complicated mathematical explanation for this. It's, you could look it up under the tennis racket problem in mathematics. But it essentially comes down to the idea that because the wing nut has a slightly offsides, it's slightly lopsided in its center of mass, that it starts to wobble slowly as it goes, right? It's not a perfect sphere. It wobbles slightly. And as it wobbles, it builds up these instabilities, and it eventually tumbles over and inverts its polarity with time. Now, it's quite interesting because actually the Russians were the ones who discovered this back in the 70s during, the great space race, right? And the Russians actually kept it secret for something like 10 years. Does anybody know why they kept it secret? You guys already know the answer, probably. Anybody else? You guys know why they didn't want to tell the world about this? Yeah?
Thought it would help them in the space race.
No, it's more dark than that. Yeah. Anybody? They were really scared that this was going to happen to the Earth, actually. And they didn't want to tell people about it. They thought, well, man, if this is what happens with rotating bodies in space, then couldn't the whole Earth essentially do this every once in a while? Now, they eventually talked themselves out of that, I think primarily on empirical reference. So they had no indication that the Earth had completely turned itself upside down several times. However, it does give us a really interesting possibility for the solid core of the Earth inverting in some sense. And so I think that's a really tantalizing possibility for what could be happening in these systems, particularly when you bring in the fact that magnets, like you mentioned, electromagnets are stabilized by iron cores. So we can amplify and stabilize a magnet by putting a chunk of iron inside of that solenoid. And a lot of your transformer systems, anybody mess around with electronics here? Any electric? A little bit? So a lot of these transformers that you build, especially if you build transformer systems, which really step different voltages between components in an electrical system. This is used in amplifiers and radio transmitters and so forth. You can really change the characteristics of your transmission by altering the metal core, and depending on whether you use a nickel core or an iron core. At any rate, the cores are always this stabilizing influence because the cores are impressionable. They'll become imprinted with that magnetic signal, and they sort of bolster it and make it stable. But if the core is in any way, either in the sun or in the earth, if it's in any way not a perfect sphere, and it's hard to imagine something perfect in nature, actually, like a sphere. Although the sun is very close. If it has any imperfection, any lopsidedness, then you can imagine a situation where you would get some sort of tumbling periodically. So I wonder if there isn't something like that going on with our central orb. Okay, so back to the solar cycles. Regardless of the mechanism by which this happens, like I said, it's still a hotly debated situation. Why in the world we go through this pattern? These dates are obviously off, but I think this is the one from your textbook. I couldn't find a better illustration of this, but what you can see is there's the actual sort of cloudy nature of the sun, these bright clouds which correspond to actual sunspots. They go through this regular pattern, right? And as it goes through this pattern, each time the north and the south pole of the sun completely reverse. So, and it's not entirely consistent. So if we count up the number of sunspots in a given year, and we track that across decades, this is from recently. I think this goes up to 2020, right? So, when I showed you guys that top-down view of our sun earlier, I was like, sun's pretty boring looking, right? because we're in one of these minimum spots right now, and we're starting to come out of it. But generally speaking, you can also see another wider trend here, which is kind of interesting, that the maximums seem to be getting weaker and weaker and weaker, right? So there's this meta pattern, this overlaid super pattern on top of the individual decade-long cycles, right? Where the overall solar activity appears to sometimes get really big, sometimes it gets really small. So if we zoom out a little bit, this is a picture of that same kind of data, but over several hundred years, right? This is really nice because, we hardly ever get data that we can look at directly from observations across hundreds of years, but people have been looking at the sunspots essentially since the telescope came online back then. And what's really interesting is that it's varied. We do see these peaks and minimums. That place back there, the Maunder minimum, is really interesting, and this cracks open a pretty cool can of worms because this period in history was known as a mini ice age, right? It was a very cold and dark time on Earth, right? And nobody really knows how in the world, first of all, whether that actually has anything to do with the lack of sunspots, or let's say the lack of solar activity, whether it's just a complete coincidence, right? So there's this really terrible, pernicious problem in science, which is the correlation causation issue. You guys heard about this before a little bit? Anybody? What'd you hear? Tell me.
Just as based on my understanding of the words alone, it's the fact, like you were saying, whether it's the Maunder minimum being caused by effects on sun or being affected by the sun, or if it was just two things that happen to have
like a mutual cause, right? I think a really good example is, and oftentimes this comes down to how good your sampling resolution is. So like, if you're like an alien that comes to study the Earth, right? And you have an instrument that can take pictures every hour, let's say. That's like the best time resolution that you have. You might, you start taking pictures of like our highways or something, right? And you start noticing, oh man, every time that there's car crashes on the highway, there's ambulances there. And so you're like, I think the ambulances are causing the car crashes. It's like totally reasonable, actually. They're always there when there's car crashes, right? But your resolution's not good enough to see that actually the crash happens first and then the ambulances show up. So you can correlate variables together oftentimes. And in this case, perhaps whatever is causing things to get really cold and dark back in the Maunder minimum, perhaps that's also causing the sun to be really quiet, and we're just not seeing the source of what's causing it. And nobody has a really killer explanation for how in the world the solar activity changes the weather on Earth. And people are working on it really hard. I interviewed this interesting lady for our podcast a year or two ago, and she had this idea, which is that the actual the distance of the planets wanders minutely, as they make their orbits around the solar system. So, guys who were in the class last time, you probably remember that actually huge planets like Jupiter, they don't exactly orbit the sun. That's not quite the right way of thinking about it. Actually, the sun and Jupiter orbit each other. And the point that's the direct, teeter-totter center of mass between Jupiter and the sun is actually slightly outside of the surface of the sun, right? Because Jupiter is enormous. So the idea is that as the different planets come into different alignments, that this center of mass is always kind of shifting, and therefore the distances between the planets are shifting. Therefore, the planets are actually tugging on the surface of the sun in different ways. And she came up with this entire idea of how this could be, in some sense, affecting not only the solar cycle, but also our climate here on Earth. So It's kind of a really tragic story because it was actually published in a really high impact, I think actually probably the most high impact journal in the world, which is Nature. And people got really upset about this because she was in some sense, I think, kind of pointing to climate change being an astrophysical phenomenon rather than an anthropogenic phenomenon, right? So being something that's a little bit out of people's control, maybe. A lot of people got really upset about this article. They ended up forcing her to retract it on the basis that she didn't include the astrophysical data about the positions of the planets as they were shifting, which is really sad because she ended up actually coming back and providing that data directly from the NASA ephemeris, which did in fact show that the positions of the planets were changing as she said that they were, but the editors were kind of like, it's too late, we can't reinstate your paper. So this paper remains retracted, which is terribly sad. Anyways, fun story of the politics of science. But something interesting is going on, right? So we don't understand it. We don't know exactly what ways the sun could be affecting the weather on Earth. Another idea that's getting a lot of attention from the folks at NASA is seismicity and volcanism, right? So just like with the Maunder minimum situation, people have been trying to tie solar activity to volcanism and seismicity. And that's really interesting as well because, there's really intense geomagnetic processes happening under our feet right now that are leading to things like this. By the way, some of the most dark periods on the history of the Earth, like the year without a summer, famously, really, really, really bad crop years. What are they tied to? They're tied to volcanoes because volcanoes tend to put all these aerosols up in the air that blot out the sun, make it difficult for crops to grow and so forth. So that might be a potential mechanism. Yeah.
Hansel and Gretel is also famously based off the year without summer.
What year was that?
1869, I have it up here.
Nice.
And it was an eruption in Indonesia.
Interesting. Hold on, I want to go back to this picture. 1869.
It happened, yeah, during the Dalton minimum. That's what I pulled it up because I was going to mention it.
Interesting. That's weird because I wonder if this axis is incorrect too, because it looks like it's like 1820s on this graph. But no worries. I mean, the point is that volcanoes are certainly a means by which you can alter the temperature on the surface of the planet. Volcanoes are incredible at screening out sunlight, basically, right? By the way, what is most of that stuff that shoots out of volcanoes? Anybody know? This is always fun. What is it? Yeah. Some of it is ash. What is like most of it, though? It's water. It's water. Yeah. So water is a great absorber of sunlight, and it will radically alter the profile. All right. Any last thoughts about all of this weird space weather interaction that nobody seems to really understand, but it's kind of cool? Yeah.
How does the water work with lava, with volcanoes?
Well, it turns out, generally speaking, you like the most famous one in our time, Mount St. Helens, right? You've seen these pictures? In that case, it was literally a situation where there was this, the magma was butting up against something approximating a water chamber inside of that thing. And it overheats that water. The water expands when it gets hot, just like a steam engine or something, and pow, blows the roof off the thing, basically. So a lot of these, especially, there was a recent one that was enormous. I can't remember the name of it. I'm going to screw it up. It was over in the Philippines somewhere, I believe. Huge one that blew up. It was actually slightly underwater to begin with. So oftentimes these cataclysmic volcanoes, they get these seawater intrusions into the magma chambers, and the water hits the magma and boom. So a lot of the explosive power of volcanoes comes from the overpressuring due to the expansion of the gases, and a lot of those gases are water ultimately. So yeah, they're really crazy, incredible stuff. We got a bunch of them around here too, which is quite fascinating. Mount Shasta is on the list of active volcanoes as far as I can tell. That's going to be really fun. Keep an eye on that. What else? Anybody? Thoughts, concerns, questions? Because I want to pivot with the back half of the class and talk a little bit, it's the last time I'm going to go on about it, but I want to talk a little bit about why people came up with this picture of the gaseous plasma sun, and I want to step through the history a tiny bit. So any last questions? Magnetism, sun cycles, solar, let's see, sunspots, anything like that? Are you good? All right. All right, I'm gonna be drawing on this paper that actually one of my friends wrote. He's actually a really interesting dude, more like a mentor than a friend, but I think I would consider him a friend. This is an interesting guy. He's actually the man who brought us the modern version of the MRI machine. So if you guys have ever been to the hospital for like something crazy, broken leg or whatever, you might have gotten an MRI, which is, I'm not even going to try to explain MRI machines to you guys right now, but it's a magnetic imaging device, essentially. And so before Pierre worked on the MRI, it was really grainy. And after he worked on it, you could actually resolve individual blood vessels and things like this. So he doubled the power of the MRI. This was several decades ago. Now, the interesting thing about working on MRIs is that MRIs are essentially, what you're doing is you're looking at light signals coming off of the body. So you excite the atoms in a certain way with magnets, and then you look at the radio frequencies that are given, so light that's given back off of the atoms in your body, and you reconstruct images based on it. So this is a dude who did not work in astronomy for most of his career, but he did work really carefully with the spectra of light signals. And he was one of the first people to really resurrect this debate about the material composition of the sun, and he's done a lot of work on it. And he was actually the chair of the radiological imaging department at Ohio State for many years, and he ended up leaving to work on this astronomy stuff. And this is one of my favorite papers by the guy. He also has a really killer YouTube channel called Sky Scholar that I highly recommend. This paper is awesome. I dropped it into your Moodle this week, and it essentially is what I'm going to be pulling from for the back half of this class, which kind of walks us through how we got to where we're at right now. And so I'll tell you a little bit about that history, but I want to make sure to really harp on 5 main points, and Pierre calls them the 5 pillars of the gaseous sun. I think it's quite an interesting way to put it, as to why we're still left with this gaseous sun, despite the fact that it's obviously producing a beautiful continuous spectrum like solids and liquids. The first time anybody even actually considered what the heck the sun was made out of is generally attributed to this Greek philosopher named Thales. This was the 6th century BC. So prior to that, almost everybody treated the sun like it was just a deity. And there's a famous story of this Greek philosopher, I think it was Anaxagoras, who tried to reason. He actually found a meteor on the ground one day, and this is perhaps apocryphal. It may not have happened, but it's an interesting myth. Apparently, he found a meteor. He saw it coming in from the sky, and he went out into the countryside and picked it up, and it was still warm. It was kind of hot still. And so he reasoned that because of this, that the sun could also be this burning, rock in the sky. And that's really the first evidence of that. There was this other philosopher named Thales who came along later and pondered about the nature of it as well and came up with a similar conclusion. But what's really crazy is that nobody really talked about what the sun was made out of for about 2,000 years after that. Give or take a little bit. The first time we really see it being discussed is in the 1700s again, which is pretty wild if you think about it. In terms of dark ages, it's hard to beat what happened between the Greeks and the Renaissance period in the 14, 15, 1600s. very, very bizarre, but perhaps beyond the scope of this conversation. So this gentleman, a French astronomer named Joseph Lalande, first posited that the sun should have some sort of structure to it. He had been reading Galileo's writings, and most people know Galileo for his heresy about the nature of the solar system, that the sun is at the center of the solar system, not the Earth. Huge debate about that. We talked about it last semester. But Galileo, it turns out, actually spent a good amount of time pondering what the sun was made out of. And so Lalande quoted Galileo, he wrote this. Galileo, who was in no manner attached to the system of incorruptibility of the heavens, thought that the sunspots were a type of smoke, cloud, or sea foam that forms on the surface of the sun, which swim on an ocean of subtle and fluid material. Galileo wrote, I'm led to this belief primarily by the certainty that ambient is a very tenuous fluid and yielding substance from seeing how easily the spots contained in it change shape and come together and divide, which could not happen in a solid or firm material. So this is kind of interesting because Galileo seems to be the first person who realized that because the sunspots are changing shape, it can't possibly just be a rock like Thales had written 2,000 years earlier, because the surfaces of rocks don't really change. And so this kicked off this era of people really starting to think about sunspots as clouds. They thought that the sun had some sort of sea of brilliant liquid on it, and that there was these nice little clouds that came and went on top of it. So, to summarize like a great deal of history, this idea of the fluid surface of the sun persisted through much of the 1700s. One of the predominant astronomers of the day was this gentleman named William Herschel, who had this to say about it. He said, "It's been supposed that a fiery liquid surrounded the sun, and that by its ebbing and flowing, the highest parts of it were occasionally uncovered and appeared under a shape of dark spots, and in that manner successively affirmed different phases. The sun, when viewed in this light, appears to be nothing else than a very eminent, large, and lucid planet, evidently of the first, or, in strictness of speaking, the only primary one of our system, the others being truly secondary to it. Its similarity to the other globes of the solar system with regard to its solidity, its atmosphere, and its diversified structure, the rotation upon its axis, the fall of heavenly bodies leads us to suppose that it is most probably also inhabited, like the rest of our planets, by beings whose organs are adapted to the particular circumstances of the vast globe." So this dude was fairly well convinced that there was people living underneath it. So, people began to actually get really good high-resolution telescope pictures of these sunspots, and they started to notice that the sunspots didn't appear to be above the surface of the sun. They appeared to be kind of like holes into the surface of the sun. Now, that was really confusing because they were dark, and so people assumed that, well, it must be cooler underneath the surface of the sun. And so if it's cooler underneath the surface of the sun, well, it may as well be people who live there, right? And that idea persisted for quite a while. He right around the end of Herschel's life, I think around the turn of the century, the 1800 century, people started to become aware of this stuff called infrared light. You guys know what this is? Anybody? A little bit. It's heat. Yeah, it's essentially the transmission of heat by light. All of us are giving off infrared light right now. Turns out we're actually giving off visible light too, but much more infrared light than anything else. So people started to study this, and Herschel realized that if the surface of the sun was really, really hot, then the people down below were going to be getting cooked by this infrared light, so he abandoned it. So, this idea persisted. People started thinking about there being this kind of opaque mass down below the surface being this, the photosphere being this luminous sea of some sort of liquid. And this persisted for, well, let's see, quite a bit into the 1800s, okay? So in the 1800s, the preeminent astronomer of the day was this gentleman named Francois Arago. And Arago was completely convinced that the sunspots must be something like, have you guys ever, has anybody ever seen lava before? Or how about molten metal in like a furnace or something like that? Yeah? You've seen it, what is it? When they melt iron down, it actually develops this kind of clot stuff on top. They call it slag, right? I believe it's the impurities from the actual melted iron. And so Arago decided that the sunspots were probably this leftover stuff. He had this to say about it. Many conjectures have been offered in explanation of these spots. Some have supposed that the sun, from which a vast quantity of light and heat is incessantly emanating, is a body in a state of combustion, and that these dark spots are nothing other than scoria, which is slag, floating on the surface. The spots, on the contrary, they suppose due to volcanic eruptions from the liquid mass. The grand objection to this hypothesis that it does not suffice to explain the phenomenon. It has not obtained admission among astronomers. The opinion most in favor of the present day regards the sun consisting of an obscure and solid nucleus enveloped by two atmospheres, one obscure, the other luminous. In this case, the appearance of the spot is explained by ruptures occurring in the atmosphere and exposing the globe of the sun to view. So, people are still thinking of the sun as something which is a flowing liquid at this point. Something really interesting happened around the end of the 1800s. So let's see if I can pull up this. Come back to this. So people started to turn their minds towards what in the world could be causing the sun to get really hot. And I'm going to jump ahead since I'm running out of time here. There was a couple of ideas about how this could work. People were also asking themselves how it was that the solar system formed in the first place, and how it was that all solar systems formed, for that matter. So when people looked out and they saw other galaxies in the sky, has anybody ever looked through a telescope and seen a galaxy before? Yeah, a little bit, a few of you. People originally called these things spiral nebula. So they didn't think they were other galaxies. They thought that they were solar systems being formed, essentially. And so people, actually it was a series of philosophers, including Kant and Laplace, who came up with this idea that what would happen is that these giant swirling balls of gas would kind of collapse on themselves gravitationally, and that this collapse would lead to the formation of a solar system. If it sounds familiar, it's because we still have the same basic idea in play today in the minds of most astronomers. Now, a very popular idea was advanced along the same time, which was that, and it was actually developed by the same people who were working on engines. So there was this new science called thermodynamics that was happening at the time. It was developed by people trying to build these heat engines. So what people realized was that if you put a lot of pressure on a gas inside of a piston, let's say inside of your car, you can actually generate a great deal of heat that way. And so this contractile idea of powering something was born, and people were actually really well convinced of it because they were starting to develop steam engines and combustion engines at this time. It was a very popular idea. Now, there was a problem with this. So the problem was that if you actually do the calculations on the sun and you treat it as a gravitational process, which is you take a gas and you squish it, sort of like you do a combustion engine, it will work. You can actually shrink the sun over the period of several million years, and you can generate enough power to recapitulate what we see coming from the sun. The problem is you'll use up the sun in about 100 million years. And so right around the same time, people had started to shift from this biblical view of time, which suggested the Earth was, 6,000-ish years old, to this Darwinian idea that the Earth was actually billions of years old. And so this idea that the sun was going to burn through all of its mass in 100 million years became increasingly untenable to people. And they couldn't go with that anymore. So that's called Helmholtz's contractile idea. So people thought that they had a good explanation for how solar systems form. They thought they had a halfway decent idea for how the sun powered itself, which lasted for maybe 100 years or so, until, well, not even 100 years, but not even an entire century, before people kind of started to look around at all of the fossils they were finding and started to really reconsider the serious timelines for our planet. There was something else that happened too. This gentleman named Andrews demonstrated that you could essentially take hydrogen, as long as it was warm, you could squeeze hydrogen, and you could squeeze it as much as he possibly could in the sort of technological chambers that they had available at the time. This is back in the 1800s. And no matter how much you squished it, it would still remain in a gaseous form. And so people all of a sudden became convinced that, well, you can have enormous pressures on a gas like hydrogen and it will still stay a gas. Unfortunately, Andrews didn't have access to this phase diagram that we now know for hydrogen, which tells us that actually if you squish hydrogen really, really hard, it does find itself in a liquid metallic form. There's also the work of Kirchhoff, which was in the 1800s. This is the guy who did all of the black body work. He also worked with this gentleman named Bunsen. If you guys ever had a Bunsen burners in high school chemistry. The two of them did almost all of the work concerning how different elements give off different colors, right? So they basically would just throw different elements inside of flames, see what colors they gave off. They would analyze them with prisms. Now, Kirchhoff did all of his work with these soot-covered chambers that he called black bodies. Unfortunately, he really, really wanted what he was discovering to be a universal principle of nature. And so in his famous works, he wrote that, not only does a solid and liquid give off this beautiful spectrum, but theoretically, if you had a gas that was under enough pressure, it would do the exact same thing. Why did they think that? Because they'd basically done these really interesting experiments around the same time. This was a guy named Plücker with his friend named Hittorf. They did these experiments where they would put these gases under extraordinary pressure, and they would look at the light that was emitted when they passed a current through them. And what they saw was that actually gases that were under pressure, they would start to emit frequencies neighboring their peak frequency. So there was a broadening of the lines, right? And so Kirchhoff, who really wanted his principle of black body radiation to be applied to the entire universe, he looked at this and thought, well, maybe it's possible that you could get that continuous spectrum if you squished the gas hard enough. Unfortunately, to this day, no one's ever actually been able to recapitulate this black body curve with a squished gas. So, all of these things together really led to this, this constellation of possibilities where people believed they had a mechanism to power the sun, which ended up falling apart, and we'll talk about that more probably next time, because we're going to talk about fusion next time. They thought they had a mechanism by which if you squished gases hard enough, you could actually get something approximating a continuous spectrum. They were never able to do that, unfortunately. They had a phase diagram for hydrogen, which is the primary constituent of the sun, that didn't get to the high enough pressures that they needed in order to see anything other than a gas. And then they had this solar system creation mechanism, which involved the collapse of a gas in the first place. So all of these pieces fit together really nicely. Now, there was at least one super boss of the day, a guy named James Jean, who was kind of the preeminent astrophysicist in the end of the 1800s in England, who really didn't buy any of this. The problem was James Jean had no alternative mechanism by which the sun could be powered. So he suggested that the sun probably was powered by some sort of radioactive process. In other words, it was full of uranium or something like that. The problem was nobody ever managed to discover light which was consistent with those kind of nuclear reactions, right? People were just beginning to realize and characterize the spectrum of hydrogen and realized right around that time the sun was almost entirely hydrogen with a little bit of helium. On the other hand, there was this gentleman who kind of popped out of nowhere around the same time named Arthur Eddington. And I think the story of Arthur Eddington is a good lead-in to fusion because Arthur Eddington was kind of like the headhunter that discovered Einstein for the English-speaking world. And Einstein is actually going to play a really important role in this saga going forward. Einstein wrote all of his papers in German. Germany was not a popular country with the other English-speaking countries around the time of Einstein. I don't know if you guys know about the two massive world wars that happened, but people in the English-speaking countries were not very happy with the Germans. So this man named Eddington actually ended up discovering Einstein's work and popularizing it and doing some of the initial proof of concepts. He also believed in this idea of fusion, and he was one of the first people who was able to say, hey, I think what's happening in the sun that could allow the sun to live for billions of years is this process called fusion, which is almost certainly the case. The mechanism by which it happens is a whole other debate. So Thursday, we're going to talk about fusion, we're going to talk about energy, we're going to talk about powering the sun, and we're going to talk about powering the earth. And yeah, have a good week, guys. I will see you then.